Welcome back. Most people think amber belongs in museums, jewelry boxes, or fossil collections. But today we're exploring a side of amber almost nobody talks about. A side that quietly influenced chemistry, industry, technology, and manufacturing for centuries. Not as decoration, not as symbolism, but as a raw material used by scientists, engineers, chemists, and manufacturers. Because long before modern plastics existed, amber was already being processed, modified, dissolved, distilled, and transformed into entirely different substances. And its chemical story is far more interesting than most people realize. Amber is not just a stone, it's a complex chemical substance. From a scientific perspective, amber is not a mineral. It is an organic polymer formed from tree resin. That means amber is made of large, complex molecular chains created through oxidation, polymerization pressure, long-term chemical transformation. Chemists studying amber have identified dozens of organic compounds within its structure. These include terpenoids, resin acids, aromatic hydrocarbons, and most importantly, succinic acid. This single compound became one of amber's most significant contributions to science and industry. Succinic acid, the molecule that changed everything. Baltic amber is especially rich in succinic acid, sometimes containing up to 8% of its mass. Why does that matter? Because succinic acid became a valuable chemical in early industrial chemistry, pharmaceutical research, dye production, food chemistry, polymer development. In the 18th and 19th centuries, chemists developed techniques to extract succinic acid from amber by heating it in controlled conditions. This process, called dry distillation, produced succinic acid, amber oil, amber resin, tar-like byproducts. These were not curiosities. They were studied, cataloged, and used in practical applications. Amber was becoming part of experimental chemistry. Amber oil in early chemical research. When amber is heated in oxygen-poor environments, it produces a dark, aromatic liquid known historically as amber oil. Early chemists were fascinated by this substance because it behaved differently than plant oils, showed unusual chemical stability, contained unique aromatic compounds, reacted predictably with other chemicals. In the 18th and 19th centuries, amber oil was studied in laboratories across Europe, not for symbolism, not for tradition, but for its chemical behavior. Some chemists used it to study combustion processes, organic volatility, chemical bonding in resins, early hydrocarbon structures. Amber helps scientists understand how complex organic substances behave under heat and pressure, long before modern analytical equipment existed. Amber in varnishes and protective coatings. One of the most significant practical uses of amber was in the production of varnishes and coatings. Amber varnish became highly valued because it formed extremely hard protective layers, resisted moisture, aged slowly, adhered well to wood and metal, provided a glossy, durable finish. High-quality amber varnishes were used on musical instruments, fine furniture paintings, wood carvings, scientific instruments. Instrument makers valued amber varnish for its durability and consistency. Furniture craftsmen used it to protect wood surfaces from humidity and wear. Restoration experts still study historical amber-based varnishes to understand how old surfaces were treated. Amber wasn't decoration here. It was functional chemistry, amber in musical instruments. This leads to one of the most fascinating intersections of science and craft: amber-based varnishes in classical instrument making. Historical analysis of certain old violins, violas, and cellos has revealed the use of natural resin-based coatings, sometimes including amber-derived components. Modern conservation scientists use spectroscopy to study these coatings in order to understand how they were formulated, why they aged the way they did, how they influence surface hardness, how they interact with wood over time. This isn't folklore. This is material science applied to cultural heritage. Amber's chemical stability made it suitable for coatings that had to last for centuries. Amber as an early thermoplastic material. Here's another surprising fact. Amber behaves in some ways like a natural thermoplastic. When heated carefully, amber softens slightly without immediately decomposing. This allowed historical artisans and chemists to reshape fragments, fuse small pieces, mold surfaces, press inclusions into artificial composites. This behavior fascinated early material scientists because it resembled properties later seen in synthetic polymers. Some historians of chemistry consider amber one of the earliest materials that indirectly inspired understanding of polymer behavior, thermal softening, structural modification under heat. Not in theory, but through observation and experimentation. Amber in the history of organic chemistry. In the 19th century, organic chemistry was still a developing field. Scientists were attempting to understand how organic compounds were structured, how complex molecules formed, how natural substances could be broken down and recombined. Amber became one of the many complex organic materials used in early chemical research. Researchers studied how amber decomposed under different temperatures, what gases it released, how its components reacted with acids and bases, how solvents interacted with amber-derived compounds. These experiments contributed to broader knowledge about organic materials long before the structure of polymers was fully understood. Amber didn't just preserve science, it helped build science. Amber in historical perfumery and fragrance chemistry. Another lesser-known area, amber-derived compounds in early fragrance chemistry. Some amber distillation byproducts were tested historically in experimental fragrance blending, not because amber itself had fragrance value, but because its volatile compounds behaved in interesting ways. Chemists studied how these compounds, evaporated over time, bonded with alcohols, reacted to temperature, interacted with plant oils. This work contributed to early understanding of volatility, molecular stability, aromatic compound behavior. Again, amber served as a research material, not a symbolic one. Amber and early plastics research. When early synthetic plastics began to appear in the late 19th and early 20th centuries, scientists compared them to natural resins, including amber. Why? Because amber represented a naturally occurring polymer that had survived for millions of years. Researchers examined hardness, brittleness, elasticity, aging patterns, resistance to environmental factors. These comparisons help chemists understand what made some materials degrade faster than others. Amber became a benchmark for long-term stability in materials research. Modern chemistry still studies amber's structure. Even today, amber continues to attract chemists. Modern research investigates polymer cross-linking inside amber molecular degradation pathways, chemical signatures of different amber deposits, stability of organic compounds over geological timescales. These studies help answer questions like, how long can organic polymers survive naturally? What molecular structures resist degradation best? How do environmental conditions affect chemical stability over extreme time? Amber is one of the few materials that offers real-world data across tens of millions of years. That's not just interesting, that's scientifically invaluable. Why this side of amber is so rarely discussed? Most documentaries focus on fossils, jewelry, history, beauty. Very few explore amber as a chemical material, but this chemical perspective reveals something deeper. Amber is not just a preserved object. It is an active participant in the history of science, industry, and material understanding. It helped shape early organic chemistry, influence coating technologies, contribute to polymer research, inspire materials. Science support conservation techniques, all without mythology, all without symbolism. Purely through its physical and chemical properties. Amber formed millions of years ago as tree resin, but its journey didn't end when it fossilized. It was heated, distilled, dissolved, tested, analyzed, applied, refined, and studied by generations of chemists, craftsmen, and scientists. It protected instruments, it shaped coatings, it inspired polymer science, it contributed to chemical understanding. It helped build knowledge about how organic materials behave across time. Not as a legend, not as a belief, but as a material of scientific importance. Amber is not only part of natural history, it is part of the history of chemistry itself. And if you made it to the end of this episode, you've just explored one of the most overlooked and intellectually fascinating dimensions of amber. One that connects ancient forests directly to laboratories, workshops, and scientific progress. In the next episode, we'll go even deeper into another hidden aspect of amber that continues to surprise researchers today.